Welcome to Module 3 of the AI and Machine Learning course. This module covers supervised learning, focusing on classification and regression. It introduces algorithms like linear regression and support vector machines, and includes model evaluation, optimization, and techniques to handle overfitting and underfitting. Learning objectives. By the end of this module, you will be able to 1. Differentiate between classification and regression tasks in supervised learning. 2. Understand and apply common supervised learning algorithms. 3. Evaluate model performance using metrics such as accuracy, precision, and recall. 4. Address issues of overfitting and underfitting and perform hyperparameter tuning. Supervised learning. Supervised learning involves training models on labeled data to predict or classify new data. It includes classification, predicting categories, and regression, predicting numerical values. Key aspects include choosing the right algorithms, evaluating performance with metrics, and optimizing models. Let's explore supervised learning tasks, algorithms, and methods for evaluating and optimizing models. Classification versus regression. In supervised learning, classification predicts discrete categories, while regression predicts continuous values. Both use labeled data for training, but differ in the type of output. Classification assigns data to categories, while regression estimates a numerical value. Both use labeled data for training but differ in the type of prediction. 1. Classification. Classification involves predicting categorical outcomes based on input features. Classification predicts categorical outcomes, either binary or multi-class. Key characteristics of classification include 1. Output. Predicts discrete classes or labels. 2. Evaluation metrics. Accuracy, precision, recall, F1 score, confusion matrix. Examples: email spam detection, sentiment analysis, image classification. 2. Regression. Regression focuses on predicting continuous numerical values based on input features. Key characteristics of regression include 1. Output. Continuous numerical values. 2. Evaluation metrics. Mean squared error, MSE, root mean squared error, RMSE, mean absolute error, MAE, R squared. Examples: house price prediction, temperature forecasting, sales prediction. Common algorithms. Supervised learning includes various algorithms, like decision trees, support vector machines, and neural networks, each tailored for specific tasks, classification or regression, and data types. Let's discuss the several common algorithms used in supervised learning. Common algorithms. Supervised learning includes various algorithms, like decision trees, support vector machines, and neural networks, each tailored for specific tasks, classification or regression, and data types. Let's discuss the several common algorithms used in supervised learning. 2. Logistic regression. Logistic regression models the probability of binary class membership using the logistic function. Key aspects include 1. Model P, y equals 1 slash 1 plus e minus, beta 0 plus beta 1 x1 plus beta 2 x2 plus beta n xn. 2. Assumptions. Linearity in the log odds, independence of observations. 3. Use cases. Predicting whether a customer will buy a product, yes/no, diagnosing diseases based on patient data. 3. Decision trees. Decision trees model decisions and outcomes using a tree structure for classification and regression. Key aspects include 1. Model. Tree structure with nodes, branches, and leaves. 2. Advantages. Easy to interpret, handles both numerical and categorical data. 3. Use cases. Customer segmentation, loan approval decisions. 4. Support vector machines, SVM. SVM finds the optimal hyperplane to separate classes, maximizing margin and minimizing errors. Key aspects include 1. Model. Finds the optimal hyperplane with maximum margin. 2. Kernel trick. Handles nonlinear relationships by transforming the feature space. 3. Use cases. Image classification, text categorization. 5. K-nearest neighbors, KNN. KNN assigns labels or values based on the majority vote or average of the K-nearest neighbors. Key aspects include 1. Model. Assigns labels or values based on the K-nearest neighbors. 2. Distance metric. Commonly uses Euclidean distance, but other metrics can be used. 3. Use cases. Recommender systems, pattern recognition. Model evaluation metrics. Evaluating the performance of supervised learning models is essential for understanding their effectiveness and making improvements. Various metrics are used to assess model performance, depending on the type of task, classification or regression. Key evaluation metrics include 1. Accuracy. Accuracy measures the proportion of correct classifications, but can be misleading with imbalanced classes. It is a commonly used metric for classification tasks and provides a general indication of model performance. 1. Formula. Accuracy equals number of correct predictions / total number of predictions. 2. Use cases. Suitable for balanced datasets where classes are equally represented. 2. Precision. Precision measures the proportion of true positive predictions out of all positive predictions made by the model. It is important in situations where false positives are costly or undesirable. 1. Formula. Precision equals true positives / true positives plus false positives. 2. Use cases. Medical diagnosis, fraud detection. 3. Recall. Recall measures the proportion of true positive predictions out of all actual positive instances. It is important in situations where missing positive instances is costly or undesirable. 1. Formula. Recall equals true positives / true positives plus false negative. 2. Use cases. Disease detection, search engines. 4. F1 score. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances the trade-off between the two. It is useful when dealing with imbalanced datasets and when both precision and recall are important. 1. Formula. F1 score equals 2 times precision times recall / precision plus recall. 2. Use cases. Text classification, information retrieval. 5. Mean squared error, MSE, and root mean squared error, RMSE. For regression tasks, MSE measures the average squared difference between predicted and actual values, while RMSE is the square root of MSE. These metrics assess the accuracy of numerical predictions. 1. Formula, RMSE. RMSE equals MSE / text, RMSE equals / SQRT, / text, MSE, RMSE equals MSE. 2. Use cases. Predicting house prices, stock market forecasting. Overfitting and underfitting. Overfitting and underfitting are key concepts in supervised learning that relate to how well a model generalizes to new, unseen data. Understanding these concepts is crucial for building robust models that perform well on real-world data. Let's discuss this overfitting and underfitting in details. 1. Overfitting. Overfitting happens when a model learns noise from training data, leading to poor performance on new data. Key characteristics include 1. Symptoms. High training accuracy, low validation accuracy, and model complexity. 2. Causes. Excessive model complexity, inadequate training data, noisy data. 3. Mitigation. Overfitting can be mitigated by regularization, cross-validation, pruning, and simplifying the model. 2. Underfitting. Underfitting occurs when a model is too simple, leading to poor performance on both training and validation data. Key characteristics include 1. Symptoms. Low training and validation accuracy with a simple model. 2. Causes. low model complexity, poor feature representation, and high bias. 3. Mitigation. Address underfitting by increasing complexity, adding features, and reducing bias. Hyperparameter tuning. Hyperparameter tuning is the process of optimizing the hyperparameters of a machine learning model to improve its performance. Hyperparameters are preset values that, when tuned effectively, improve model accuracy and generalization. Let's discuss some key aspects of hyperparameter tuning. 1. Grid search. Grid search involves specifying a range of values for each hyperparameter and systematically evaluating all possible combinations. This method exhaustively searches the hyperparameter space but is computationally expensive. Procedure. Define a grid of hyperparameter values, train and evaluate the model for each combination, and select the combination with the best performance. 2. Random search. Random search samples random hyperparameter combinations, making it more efficient than grid search for high-dimensional spaces. Procedure. Define distributions for hyperparameter values, randomly sample combinations, train and evaluate the model, and select the combination with the best performance. 3. Bayesian optimization. Bayesian optimization uses past results to efficiently find optimal hyperparameters by balancing exploration and exploitation. Procedure. Define a probabilistic model of the objective function, iteratively update the model based on past evaluations, and use the model to select new hyperparameter values to test. 4. Cross-validation. Cross-validation assesses model performance by repeatedly splitting data into training and validation sets, helping prevent overfitting. Procedure. Split the data into k-folds, train and evaluate the model for each fold, and average the performance metrics to select the best hyperparameters. Summary. This module covered supervised learning, focusing on classification and regression tasks, and explored key algorithms like linear and logistic regression, decision trees, SVM, and KNN. We also discussed evaluation metrics, overfitting, underfitting, and hyperparameter tuning, providing the foundation to develop and assess supervised learning models. Congratulations on completing the module. You've gained the skills to apply supervised learning to optimize processes, enhance efficiency, and develop intelligent solutions, setting yourself up for success in the digital era. Keep up the excellent work.